So here we go. If we're drawing a force diagram for our soccer ball while it's in the air and a motion map for its trajectory, what we're going to be looking at is sort of the shape that goes across the space if we're thinking about it in terms of height and distance. So over here, since we don't have any data, we don't know how long it's in the air, I'm just going to pick a couple of spots and make points there for this force diagram part. It goes up, gets to the peak, comes back down. I don't even know if that's even, but we're just going to go with it. Dr. O'Malley wasn't very specific with where this should be, so there we go. That's what we're getting. So if I choose these locations for my soccer ball, what forces should my soccer ball be experiencing? Just gravity, right? That's it. It's not getting kicked while it's moving through the air. Nothing's happening to it. It's not going, there's no sideways forces. There's no up and down forces. The only thing that's impacting this object because it's in the air is gravity. And that's it. Nothing else. Nothing else. Do you guys have any questions about that one? Don't get fooled on the things that are in the air with nothing touching it. If it's not interacting with anything, there's no other forces. It's only interacting with the earth. For motion maps, if I wanted to do a similar number of dots, and there's really nothing stopping me because, again, the teacher who wrote my worksheet did not say, hey, you need to have 15 dots. I'm just going to draw a couple. All right, I'm going to put one here at the beginning too. Okay, so kind of like this. All right, so if I have this happening and I need to figure out what my motion map is like, I need to draw vertical and horizontal arrows that represent vertical velocity and horizontal velocity. So vertically, what's going to happen with this thing is that we're just going to draw, no matter what we're looking at, we're just drawing arrows that are half the distance between the points. So here we're worrying about the vertical distance, and this is on a grid, so that makes it kind of nice. So I know that I'm going to draw a line that goes halfway to that point. There we go. For the second one, I'm going to go halfway to the line where I put, come on, buddy, to the line where I put my third dot. So it's going to extend halfway to that line. You might notice they're getting shorter, right? Up here, the next dot is down here. This has no vertical velocity, but I wouldn't blame you guys either if you drew an arrow going downward, because it's going to start to go downward as soon as it leaves that center position, right? And then this one's going to be halfway down. And then I could imagine that this would extend this way, and I could draw my next arrow down that way. So there's my vertical velocities. So my velocities here are going to be moving upward, right? Because my object is moving up. And then when it starts to come down, the velocity is also negative. Horizontally, we're going to do the same thing. We're just going to do half the distance between the points. I maybe didn't do a great job of this because they should all be equal, right? Maybe this dot needs to be like up here a little bit more. But with these guys, I'm going to draw a line that's halfway between the two. Actually, that like really bothers me. I'm going to fix it and add some more dots to mine. You may have done yours better than I did, but they should be equally spaced across there. So I'm going to draw one here, 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 here. And they should be all about the same length. I wrote they should be equal. If you're ever worried that I'm not gonna recognize the thing that you're trying to show me, you can feel free to put a note in the margin just to make extra sure. And for those two dots that I added, I'm going to add some vertical lines. So now maybe this shouldn't be so high, but this one can be shorter. This one should be definitely shorter. So it can be a little bit longer. There we go. I feel better about that. You guys have any questions about the motion map or the force diagrams? Any questions? No questions? All right. So yesterday we did number 2 together. The third problem says a lacrosse player slings the ball at an angle of 30 degrees above the horizontal with a speed of 20 meters per second. How far away should a teammate position herself to catch the ball? Okay. So firstly, we're going to imagine that the height above the ground that the ball is released is the same height that it's going to be caught. So I'm going to draw a line that represents that point. Here's the ball. The ball's getting released at an angle of 30 degrees. So I'm going to go up 30 degrees. Release the ball. And it has a speed of 20 meters per second. And it's going to travel some distance. And then the teammate is going to catch the ball over here. Oh, this camera is killing me right now. All right. So what we need to find is the distance all the way across here. What is that range? We start with a little bit of information here. We're going to have to decide if we want to calculate for all the way or if we want to go up to the center point up here. Because we know stuff at both of those positions. If we're looking at our center point, we know that at that point, our vertical velocity is 0 meters per second. We can solve for the half time. We can figure out the range. We know that the acceleration there is minus 10 meters per second squared. So that's 2 pieces of information, along with finding this vertical velocity. So this is going to be our initial vertical velocity. So we would know 3 pieces of information. We could also look at this point and say that our change in height is going to be 0 meters per second. Sorry, 0 meters. Wow. 0 meters. We know that acceleration is still minus 10 meters per second squared. And so we could solve for time and then use time. We're going to need to solve for time either way, but use time with the horizontal velocity, which is going to be this. So we know for sure that we're going to have to divide our initial throw into components. We have to solve for time. And then we can solve our final problem. So the first thing we're going to do is find the components of the throw. So in order to do that, we've done this problem a bunch of times. Our initial vertical velocity is going to be 20 meters per second times the sine of 30 degrees. I like to imagine them all relative to the angle that we're actually given. And so this side is going to be congruent with the opposite side of this triangle. And so that relationship is going to be the sine of the angle. If we solve for that, 20 times the sine of 30 degrees, it's going to give us 10 meters per second. And our initial horizontal velocity is going to be 20 meters per second times the cosine of 30 degrees. For 17.3 meters per second. So those are our initial velocities. And I can then start making a list of things that I know, things I have to solve for. So my initial horizontal velocity is going to be 17.3 meters per second. My initial vertical velocity is going to be 10 meters per second. I know acceleration is minus 10 meters per second squared. I know that if I call this point right here, I put t, this is a t, and then 1/2 as a subscript because it's half the amount of time of the throw. And so if I use that, I can keep track of stuff, and I can also call this stuff things like vy 1/2. So the next thing we were going to do is solve for time. I like to use this one. And the reason, let's see, the reason that I like to use this one is because I can avoid using a quadratic. So I don't know. I am less likely to forget to do a square root or something. So because what I know at that point is 2 velocities, my initial and final velocity. I always know acceleration, then I can solve for time. And that's relatively straightforward, especially when my initial velocity is 0, which isn't the case here. But the second thing I'm going to do is solve for time. So to solve for time, I'm going to use my idea that the velocity at 1/2 vertically is going to be 0 meters per second. So my final velocity is equal to my initial velocity plus acceleration times time. Here my final velocity is 0 meters per second. It's equal to my initial velocity, which was 10 meters per second, plus minus 10 meters per second squared times time. So if I subtract 10 meters per second from both sides, I have minus 10 meters per second equals minus 10 meters per second squared times time. So time equals 1 second, which means it takes 1 second to get to the top. If it takes 1 second to get to the top, how much time does it take to get all the way across? 2 seconds, yeah. So my time here is 2 seconds that it takes to get across. So the last thing we can do is solve for the range. So the range is equal to horizontal velocity times time, which is going to be 17.3 meters per second times 2 seconds, which is going to be 34.6 meters. How'd you guys do on that one? Did you get it? You guys have any questions? No. You guys ready to do the next one? Number 4. A ball is thrown straight upward and returned to the thrower's hand after 3 seconds in the air. A second ball is thrown at an angle of 30 degrees with the horizontal. At what speed must the second ball be thrown so that it reaches the same height as the one thrown vertically? So we're going to have 2 balls. One ball gets thrown straight up and then comes back down. The other one gets thrown up in the air at an angle of 30 degrees. Draw my picture here. And it gets the same height. All right, so it's saying that the heights are the same. And we're asked to find what speed the second one has to be thrown at so that it reaches the same height. So we have to solve for that velocity. That's what we're trying to figure out. So what do we know? I've got these in blue and green. Can you tell if they're blue and green? Maybe a little. See if I zoom in if the color is better. Maybe I need to get like one of those clamping desk lamps so that it's the right color. I'm gonna try something. Experiment time. Did I make it any better? Not really. This looks treacherous, Carson. It's not gonna hold it up. I'm like thinking like maybe I can take my books and stack them up. It's not gonna work. Okay, so with the ball, what we're gonna do is use this first one to figure out how high the ball went in the air. Wow. Okay, so if we want to figure out how high it went, we know that the acceleration is minus 10 meters per second squared. We know that the vertical velocity at the top is going to be 0 meters per second. We know that at the top it takes, so we know at that point right there that we've got 0 meters per second. And we know, I'm going to make this y 1/2. And we know that the time at that point is half the time, which is going to be 1.5 seconds. So if we use that information, we can figure out how high it went. How high is our change in y? It's going to be equal to 1/2 times acceleration times time squared plus initial velocity times time. Oh no, we don't have our initial velocity, do we? Bummer. We'll use a different one. Dr. O'Malley picked the wrong equation. I'm going to do it the other way. What if we do it this way, guys? How'd you guys do on this problem? Did it make sense to you? Some of you liked it, some of you didn't like it. Here's what I think I want to do. I'm going to treat this like the initial position and just look at the second half. Right? So if we look at the second half, then we can call this top one the initial. I think that will work. And if it's the initial and it's 0, then we don't have to worry about it. So that change in height is going to be 1/2 times minus 10 meters per second squared times time squared. And we know that the time is 1.5 seconds. Come on, whiteout. This whiteout is so much better than when I was a student. You had to like let it dry, wave it. It's terrible. And that has to be squared. So we're going to do 1.5 times 1.5 times minus 10 times 0.5. So our change in height here, I got minus 11.25, which makes sense because we were calculating it for when it was falling, right? When it was moving downward. So the other thing that we need to know now is our to get that height, we need to know what vertical velocity, what vertical component of velocity we need. And so let's see, what is our initial vertical velocity? Because that's what we're going to need to use to solve the second part of the problem. So to figure that out, now that we know the height, we can use something else and figure it out. So I don't know, which ones do you guys like better? This one work. 0 equals initial plus acceleration. I think that we could use that one. So if we use our final velocity and use that peak as our final velocity, and we want to solve for that initial. So if this is 0 meters per second equals the initial velocity plus our minus 10 meters per second squared times 1.5 seconds. Then 0 equals our initial velocity minus 15 meters per second. So the initial velocity equals 15 meters per second. So that tells us our velocity at this point. All right, 15 meters per second. But that one is straight up and down. And so if we want to solve for this green one, solve for velocity at the 30-degree angle. In order to do that, we're just going to have to use our triangle, right? If this one up and down is 15 meters per second, we want to know what this one is. And we know that our angle here is 30 degrees. So if we wanted to use our 30-degree angle, the triangle that we would be looking at is this triangle. So the relationship there would be the sine. That the sine of 30 degrees is equal to that 15 meters per second divided by our hypotenuse, which is our question, right? That's the one that we're trying to solve for. So to solve for that, we would switch it. Switch places here. So 15 meters per second divided by the sine of 30 is going to give us I got 30 meters per second. Does that make sense? I don't know if I like that answer. What'd you guys get? That's right. If Maddie says it's right, I kind of trust it better. Okay. Just so you guys know, I don't like problems like that, so don't expect that tomorrow. Okay. You guys have any questions? No? All right. How are we doing on time? We're doing okay. All right. For number 5, it says 2 objects are initially the same height above the ground. Simultaneously, one is released from rest and the other is shot off horizontally with an initial speed of 2.5 meters per second. The 2 objects collide after falling 20 meters. How far apart were the objects initially? So we've got 2 objects, right? One of them is going to get shot off to the side, and the other one is going to be dropped straight down. What we have to figure out is how far they are apart initially, what this range is. Okay, we're told that that happens when they've fallen for 20 meters. Right, so that's when our change in y is equal to 20 meters. So really that gives us a clue. We don't really have to think too much about this one that dropped straight down. We just have to think about the range of the one that was shot off to the side. So we know that this one went off to the side with a horizontal velocity of 2.5 meters per second. And that's all we know. All right. So let's see what we know about our horizontal variables and our vertical variables. So our horizontal variables, we know that our velocity is 2.5 meters per second. We don't know how long it traveled that distance yet. We could solve for it. And we don't know what the range was. We do know that the displacement vertically was minus 20 meters. We know that acceleration was minus 10 meters per second squared. And we know that the initial vertical velocity for both of those was 0 meters per second. Since we know 3 things there, we can solve for time and then use that to solve this problem over here. So the first thing we're going to do is solve for time. Best way to do that with the information that we have is that quadratic formula that we love so much. It's so handy. Our initial velocity is 0, so yay, we can get rid of one of the terms. So now we've got minus 20 meters equals 1/2 times minus 10 meters per second squared times our time squared, which is the unknown thing that we're trying to solve. So minus 20 meters equals minus 5 meters per second squared times time squared. Time squared then equals 4 seconds squared. Oh, this one we can do in our heads, guys. So time equals 2 seconds. So if we've got 2 seconds and we want to solve for that change in displacement, then to do that, we just have to multiply our horizontal velocity times our time. So we've got 2.5 meters per second times 2 seconds. And we find that they're a distance of 5 meters apart. You guys have any questions about that one? No questions. You guys are quiet today. All right. Frustrated with history because you'd never get frustrated in physics class, right? Never. Not once. You open the second story classroom window, and to the horror of your teacher, violently hurl your history book out the window. You guys ever done that? Thrown a book out a window? They kind of flutter to the ground. With a velocity of 18 meters per second and an angle of 35 degrees above the horizontal. If the launch point is 6 meters above the ground, how far from the building will the book hit the parking lot? Okay, so first we have to kind of draw a picture about what's happening here. So here's our building. Here's our student. He's about to chuck a textbook out the window. The launch point is 6 meters above the ground. And this thing is going to get launched 35 degrees from the horizontal. So there's our 35 degrees. And there goes the book. Poor book. I even love history books. Okay, so our initial velocity here is going to be 18 meters per second. We have some stuff to figure out. Ultimately, what we're trying to find is our horizontal distance. This is very doable. Let's make a list of the things that we know. What do we know horizontally? Not much. We need to figure out what our horizontal velocity is and what our vertical velocity. Time, then we can solve for our distance. So let's take a look at this guy. We know that when this thing hits the ground, that the change in height is going to be minus 6 meters. We know that our acceleration is minus 10 meters per second squared. Anything else that we know? Well, we're going to need to figure out what our initial vertical velocity was. That will help us. So over here with our initial velocities, our components of velocity. Here's what a triangle looks like. Right, here's our horizontal velocity. Here's our initial vertical velocity. We've got 18 meters per second and an angle of 35 degrees. So our horizontal velocity is going to be that cosine relationship because it's the adjacent angle and the hypotenuse. It's going to be 18 meters per second times the cosine of 35 degrees. And our vertical initial velocity is going to be 18 meters per second times the sine of 35 degrees. So for those two, do 18 times cosine of 35. I got 14.7 meters per second. And then for the other, I got 10.3 meters per second. Copy these down here on my list. I also need time. Okay, so if I want to solve for time, take a look at my list. I've got distance, acceleration, initial velocity, can solve for time. It looks like that what I'm going to have to use is my quadratic one. And unfortunately, I'm going to have to keep this because I can't get away from my initial velocity here. So we've got to do minus 6 meters equals 1/2 times minus 10 meters per second squared times time squared plus my initial velocity, which was 10.3 meters per second times time. If I add 6 to both sides, of 0 equals minus 5 meters per second squared times time squared plus 10.3 meters per second times time plus 6 meters. Oh no, quadratic stuff. You guys like the quadratic stuff? Extra steps, right? So to solve for this, we're going to have to say t equals, and then do the minus b plus or minus the square root of b squared minus 4ac all over 2a. So do minus 10.3 plus or minus the square root of 10.3 squared minus 4 times minus 5 times 6 divided by 2 times minus 5. All right, so if I do the plus, I'm going to get one answer. If I do the minus, I'm going to get a different answer. So I'm going to pull out my calculator. So inside this is going to be, let's see, 10.3 times 10.3 is that guy. 106.09. And then I've got minus 4 times minus 5 times 6. So it's going to be plus 120. So if I, let's see, 120 plus 106.9. So I've got 226 that goes in here. I'm going to find the square root of that number. 15. So it's going to be minus 10.3 plus or minus 15.03 divided by minus 10. All right. So 10.3 plus 15.03 equals 25 divided by minus 10. So if we use plus, then our answer is going to be minus 2.533, which doesn't seem right because it's positive, right? If I do minus 10.3 minus 15.03 divided by minus 10, the answer I get is 2.533. I don't like those answers. Did I do something wrong somewhere, guys? I don't like them because they're the same. I feel like one should be much less.
I think in the first one you forgot to put the negative, but there was 10.3 in your calculator.
Cool. Okay. Let's try that. 10.3 and then plus 15.03. Yep, that's it. Thank you very much. I'm telling you guys, sometimes if answers don't come out right, you probably messed it up somewhere. Wow, really? That seems wrong. Oh, I multiplied it. See, I did it again. I messed it up again. Divided by minus 10. There we go. So this one would be minus 0.473. The reason I knew that answer wasn't coming out right, guys, so I got minus 0.47 and 2.5, is because one of those numbers is going to be describing the amount of time that it takes for it to fall. The other time would be describing if the book went backwards on the same trajectory. And so I was expecting one number to be much smaller than the other one. And the smaller one should have been the negative number. And so that's why when I looked at this and I got the same number, I thought, that's not right. And you just want to make sure that the one that you're going to, I was pretty sure I wasn't going to use the negative number, so maybe it didn't matter. But I needed to make sure that I had the right ones to choose from. But this one is the correct one. So I'm going to choose my 2.533 seconds, 2.533, and then to solve for the distance, that's going to be just multiplying these two together. So it's going to be, I'm just going to stick it down here. So my change in position is going to be 14.7 meters per second times the 2.533 seconds. So 14.7 times 2.533. That gives me 37 meters, 37.2 meters. So if you saw this kid do this, would you try to recruit him for the baseball team? If he throws a book 90 feet, I would too. How far is it from the pitcher's mound to home plate? Is it 60 feet? No. You were nodding like you were a baseball player. No. I think it's 60 feet. Might be 90. Is it? I might be conflating that with the distance between the bases. Anyway, what questions do you guys have? Any questions? Neve. No, because what I am most concerned about is that the reasoning was sound. So keep the things that you think you should have. If I would, if you're given a decimal place up here, keep the same number of sig figs.
Yeah, I just rounded time to 2.5 instead of 5.
Yeah, honestly, I probably kept more sig figs here than I actually need. Okay. Because all these numbers just have 2 in them. So I could have written 37. I could have written 15. 15 feels weird though because that's really close to your initial. But Yeah, I'm looking more for making sure that the reasoning is good instead of, did the student get the right sig figs? Honestly, I don't care about sig figs. Don't write like 15 digits. You won't. I don't. Nobody does that in physics. It's more likely to happen in chemistry. Um, but I'm just looking for, does the reasoning make sense? And so what's more important than like the number of digits you show or like worrying about, you know, can I use -10 or -9.8? I don't care. I usually write my key with both. I care more about, is your reasoning there? And so it's more important that you actually show your work. I know there are some folks that really like to just do it in their calculator, but showing your work helps me a lot with making sure that you did that. So if you get to the end and it doesn't quite make sense, if your work is there, it's easier for me to give you points for your work. You guys have any questions? Oh, we still have time left and stuff. Whew. Guys, we're gonna make it to spring break. Aren't you excited? My children are counting down. Like they tell me multiple times a day, Mom, we have 2 days. And my kids already had spring break. They had spring break last week. They're like 2 days back from their spring break, and they're already like, Mom, in 2 days we get a 4-day weekend. I'm like, good for you. I get a 10-day weekend, and they're like, that's not really a weekend. It's like a whole break. I know. Ah, kids.